Well, good evening to all of you gathered here. Sir, shall we begin the webinar?
Yes, absolutely. Okay, so go ahead, please.
Let me just say a word of welcome to all. We have in our participant list mostly students from the college itself and a few others from others outside this college. Well, welcome to one and all. And let's have a very fruitful and resourceful session now. Thank you, Apparao sir, for coming back and taking great efforts for this second session. Well, welcome, sir, and thank you for the resourceful session. So please.
Okay, thank you so much. So let me begin by apologizing for the hiccups we had during the first attempt. So I'm glad to be here, and thank you all for joining on a Saturday. You could be doing better things than listening to my talk, so I greatly appreciate your participation. And like I told Benoit, I kept this talk at a very basic level. So please, as and when you have any questions, please put it in the chat box, and I will try to leave ample time for Q&A, question and answer session. Okay, so let's begin by understanding why we need to improve batteries, or why we need batteries at all, right? So as most of you are as most of you already know, that current battery technology is the lead acid battery in most cars, right? So the car engine works on, it's basically an internal combustion engine, which is called ICE or ICE. And basically to ignite the fuel, you need the lead acid battery. So the role of the battery is quite small, right? In comparison to the gasoline. And so now what we want to do, because of climate change and also dependence on oil resources and so on and so forth, which all of that is called fossil fuels, including coal. When the electricity is also generated by burning coal, all these are having adverse impact on environment. So one of the big push here is to transition away from fossil fuels. So how do we do that? We do that by developing batteries. And this is a major thrust at Clemson University. So Clemson University is in the southeastern state called South Carolina. And we were established in 1889. And in that university in 2013, I established this Nanomaterial Institute. And the reason for doing that is because nanomaterials, because of the very small dimension, 10 to the minus 9 meters, they have new properties that the bulk don't have. And so the whole game here is to exploit such amazing properties of these nanomaterials to solve problems like the one I just outlined, climate change. How can we move away from fossil fuels? Okay, so and so we just talked about the lead acid battery in the car here, right? But in addition to that, batteries are used in a number of applications that you see on the screen, right? Right from the time you get up, look at your cell phone, brushing your teeth, so on and so forth. And of all the other battery technologies, there are many, like I'm sure most of you have heard about the nickel cadmium batteries and so on. So what we are finding is that the lithium ion chemistry is the best. So what we mean by that is it gives the battery the ability to store a lot of charge compared to other batteries technologies, okay? Like for example, nickel cadmium. And so lithium ion batteries is at the heart of taking us to the next generation power or energy storage. And so one of the grand challenges, not only in the United States, but across the world, and in India, Tata Motors are leading the effort where we eventually want to get electric vehicles everywhere. So EV here means electric vehicles. So in short, you want to electrify the transportation system in your country. Okay, and in order to be able to do that and compete with gasoline, there are a certain number of parameters that we have to satisfy, okay? And those parameters are understood as spider plots. So what you're seeing here is a spider plot. It reminds you of a cobweb, right? At each point here, these are the metrics that one needs for a good battery for automotive industry. You need an energy density of 500 watts per liter. So this is volume. You can think of this battery as a box that has a certain amount of volume. And then, different areas have different temperatures. You want them to function over a wide temperature range, and you want to charge them quickly, right? You don't want them to take forever. Right now, it's overnight charging. So can we cut this down to a quick charge and use over an extended period? And most importantly, cost. So right now, Tesla, I'm sure most of you have heard, they have established what's called a gigafactory. Giga is 10 to the 9, right? Billion. So they are producing billions and billions of these lithium ion batteries, but the cost of the battery pack, so all these batteries are assembled into a pack, and the pack goes into the automobile, right? There is no gas tank. Instead of the gas tank, you have this battery pack. The battery pack costs as much as the cost of another automobile. So it's extremely expensive. Okay, so we want to cut that down. Can we do that? And of course, we want to use the battery as many number of times as possible. So, about 1,000 cycles or more, so that the battery pack can be replaced every 3 to 5 years, right? You don't want to replace every year. It's too expensive. And so here, this is the life. That means the batteries should have good shelf life. If I make it today, and they should not degrade over at least 5 years or even 15 years is very ambitious. And they should have very good energy, specific energy. I'll talk a little bit about all of these as we progress, okay? So these are the parameters that one needs, and a lot of research has gone into this to identify these parameters that you see as a spider plot. If we can get there, then we have a chance of displacing gasoline. That's the basic point. And this is established by US Advanced Battery Consortium, okay? So an overriding factor of all of this, of course, is the safety. You have seen several videos where lithium-ion batteries in cell phones catch fire. The user is totally unaware, and all of a sudden the cell phone in his or her pocket catches fire. Then there is also some incidents about Boeing, the batteries catching fire and cars catching fire. So safety is an overriding factor of all of these. So this is what we want to achieve. This, or we call it the grand challenge, okay? So before we dive into, how we can address this grand challenge, let's try to understand basic operation of a battery. So, you have seen ever-ready batteries, right? So they have a button kind of end and then a flat end over here, okay? And so this side is a positive side, this side is a negative side, and usually the positive side has the lithium containing material, okay? And in this case, it happens to be either the lithium cobalt oxide or lithium iron phosphate. So these are oxide-based materials. And on the negative side, you have graphite. Okay, so each of these dots that you see here, the black dot, is a carbon atom. And these carbon atoms are arranged as layered materials. So there is a gap between these guys. You can see the gap. And that gallery space is very important because what happens is when you plug, let's say such batteries are in your automobile, right? And when you plug your automobile for charging, so the lithium ions during the charging phase, okay, so this is the initial phase. So you plug in your car to charge, the lithium ions move from the oxide materials, they move into the graphite, and the electrons move from the external circuit, okay? And then when you are completely charged, all the lithium is stored in your graphite, as you see here. And now you're ready to use the car. So you drive the car, you're basically discharging the batteries. And in a perfect battery, this reaction is reversible. That means the lithiums will go back and the electrons will flow through the external circuit and either light a bulb or run a power drill or drive a car. So this is the basic mechanism. And in order to prevent this positive and negative side from shorting, you have what we call the separator. So this separator is quite unique. It allows only the ions to go through, and you don't want electrons going through here. So electrons are forced to go through the external circuit so that you can utilize them to the maximum extent, okay? So this is like a 1-minute summary of how a battery works. And the other thing that you see here, the blue, is the electrolyte, because the lithium ions are usually obtained from salts like what we call LFP, or lithium phosphorus and hexafluoride here. And the organic solvents are ethylene carbonate. So they look like this. So this is your ethylene carbonate here, and this is your salt. At the center you have phosphorus and fluorine there, and this is a anion, this is the cation, and that's your salt, okay? And this has been actually, these salts have been discovered in the 90s, and or even before, I would say in the 60s, but it took about 30 years before they could be converted into a coin type cell. That was done by Sony, a company in Japan, right? And recently in 2019, this technology advanced to such an extent that without these batteries, we cannot exist, right? So that's the current status of humanity. And so very deservedly, it received the Nobel Prize in 2019. Okay, so this talk is going to focus mostly on the lithium-ion battery. And like I said, Sony commercialized this in 90s. And for a Tesla electric vehicle today, it requires more than 7,000 cells. So imagine the weight of 7,000 ever-ready batteries. It weighs more than a ton or so. And that's obviously not ideal. So going back to that spider plot, if you can increase the energy density, then you will need less number of cells. That is the idea. Okay, so this is a snapshot of the battery landscape as of today. So lead acid battery, I said a little bit about it. I talked a little bit about this one, nickel cadmium, and then there is this mercury based, and there is only lithium ion, and then all the others that are in the color other than blue. Blue means all these are available technologies as of today, and a Nissan Leaf uses this kind of technology. You can drive about 100 miles or 160 kilometers on one charge. So again, in the spider plot, you want to be able to drive at least same distance as the gasoline tank would allow you to drive. So in this country, an economy car like what you're seeing here, if with one fill, like economic car gas tank can hold about 10 gallons, you can drive about 300 miles. So this is only 100 miles. So it is 1/3 the capacity that the gasoline car can offer. So these are real world problems. And to solve these real world problems, we need basic research. Okay, so that is the beauty about studying topics like physics and chemistry and mathematics. Fundamental science basically drives innovation. That's my favorite tag, which I always keep telling at Clemson University. While engineering is great, you see the final product, but what really drove it is fundamental science. Right? Okay, and so these are the new batteries that are under development. And this lithium air is still at the lab phase. What I mean by that is you all know that alkali metals catch fire as soon as they are exposed to air, right? So it is good and bad. It's good because immediately they can release a lot of energy, but how do we tap into that energy to drive a car is still at the research and development level. That's why this is R&D. Whereas these have advanced to a level where we can make a coin cell. I will show you an image of that. You know, these are basically button type cells that we put in watches and so on. So we know how to do this. So these are under development. And so my team decided to work on the highest of these three, which is the lithium sulfur. So we will not only be talking about lithium battery today, but we'll be talking more specifically about lithium sulfur battery. And I'll tell you why that is interesting and why that is important, okay? All right, so let's move on. So again, that's the goal. And I will tell a little more about that as we go on. So we saw what a battery is. We saw very basic operation of a battery through that animation. Now we also need to understand a couple of other terminologies to further understand batteries. So in future slides, you will hear me say something called a C rate. So C rate is nothing but a charging rate, C for charging. Okay, and then you will also hear me say a lot of times capacity. Capacity basically means the amount of charge that electrode can store. Okay, so that's very fun, very simple. And sometimes you will see plots where I say specific capacity. So specific capacity means basically amount of charge stored per unit area or amount of charge stored per unit volume, like we saw in the spider plot. So just bear that in mind. So these are very simple terms. So what or how is the C rate defined? So 1 C rate means, which is in bold, 1 C rate means that I can charge the battery in 1 hour. Okay, I don't have to do overnight charging. So right now, the batteries are charging at 1/10 the C rate, okay, or 0.1 C rate. That's why you need overnight charging. But we want to get here. We want to charge under 15 minutes. So 5C means very fast charge rate. Okay, so basically what you do is you take 60 divided by the number before C is approximately the time it will take to charge or discharge the battery. That's what that C rate is. Very, very simple. And capacity, like I said, is the amount of charge. So the units are milliamp hour. So milliamp is basically coulomb per time, and that cancels with this hour. So this unit is coulombs. But the battery industry lists it, instead of saying coulombs, they write it at milliamp hour. All batteries are rated as milliamp hour. Okay, and this capacity depends mostly on the mass of the active material. So what do we mean by the active material? So in that animation, you saw the lithium ions are moving back and forth, right? So lithium ions are the active material in the lithium ion battery. And you can also say that the lithium ions cannot move nicely, like you saw in the animation, if the graphite cannot accommodate them properly, right? If so graphite is also an active material, all right? And likewise, the host, the oxide host, lithium cobalt oxide in the animation that you saw is also active material, okay? So number of parameters have to be just tuned properly so that you have the best battery that you can envision. Okay, so let's take another one slide tutorial on how we can estimate the capacity of new materials, okay? So basic chemistry, right? I mean, so this is lithium ions, and this is the lithium ions that are moving in the electrolyte, as you saw in the animation. These are the electrons that flow in the external circuit. And graphite has a honeycomb lattice, right? It has the C6 units. So the basic reaction is that if everything goes well, it can accommodate to a point where you get a lithium compound, which is called LiC6, okay? So basically, the takeaway point here is for every lithium ion that you're storing in graphite, you get one electron to be used in the external circuit. That's how you should read this equation. So obviously, there are therefore other chemistries that people are trying. They are using alkaline earth materials. Why? Because they can give you 2 electrons. And my team has even developed an aluminum ion battery. Why? Because aluminum can give me 3 electrons. But there are other problems which I won't go into details today, maybe some other time if there is continued interest in battery research. So you want to maximize this, right? And therefore you want to explore different chemistries. Okay, so the way capacity is calculated is given by this formula, very simple formula. X is the number of electrons which you want to maximize, but here in this case it's only 1. F is the Faraday constant, which is right there, so many coulombs per mole. And then the N is the number 6 here in this equation, and C is the for carbon, so many grams per mole for carbon. So for graphite, if you crunch the numbers, you will get about 370 milliamp hour per gram. So this is the theoretical capacity. In real life, you don't get that much. You get much less than 200, because there are a lot of real world challenges, okay? But this is the maximum that you can get. All right, and then this is on the lithium side, right? But what about on the cathode side? like the lithium cobalt oxide. So for the lithium cobalt oxide, this is the reaction. It only gives you half an electron. And then the specific capacity is this number that you see on the screen here, okay? So lithium cobalt oxide has a capacity, but why we want to go for lithium sulfur? Um, the reason is that sulfur has a theoretical capacity which is much greater than the lithium cobalt oxide. So on the previous screen you saw the number, and see if you do the same exercise for sulfur, you get 10 times more. This sounds very exciting, but there are a lot of problems. Number one, sulfur does not conduct. Then you say, okay, no problem, I can add carbon additives like carbon black, and then I can, these are conducting additives. Then I can, this comes as powder, so I can make a slurry or a paste using polymer binders. So I can make an electrode, materials scientists would say that. But then what you have just done is you have increased the amount of inactive material in your cathode, because this carbon additive does not store the lithium ions, neither does this. So you have dead weight in your electrode. And remember, one of the goals is to reduce the weight, right? Your weight of your battery. But by going this route, so you say, this is so good that I'm going to pay a small price here, okay? And so people have done that. We have also made these kind of batteries. And the minute you assemble such a battery with a lithium anode, this is your lithium anode, and you have your electrolyte here, then of course you can get, during charging and discharging, you can get the current to flow in the external circuit. Not a problem. So, but let's see what happens, okay? So moving on to the next slide. And likewise, the lithium has a very high theoretical capacity. So it looks like a problem worth chasing. And that's what the battery industry has done. So how do they do it? So they basically take an aluminum foil for the cathode. This is the cathode and this is the anode here. So the slurry is made by mixing all these guys, and then you use a doctor blade, or you spread it on the aluminum foil, let it dry, then you use stamping. You cut out a circle, and then this is your anode, lithium foil. This is your cathode, which will be the aluminum foil with this slurry here. And then you have to put a separator so that they don't short out. And then we use some mechanical springs here to make sure, everything there is no loose parts in this cell. And then we use a crimping machine like this one, and we make a coin cell battery. And of course, you can't do this in air because all these are air sensitive. And I don't know whether you can see very well, but here is a crimping machine inside a glove box in my lab. So we do all of this inside the glove box, and then we use cyclic voltammetry. We can put, do what we call current versus voltage plots. And I won't again go into all these details. This is standard electrochemistry for testing these electrodes, okay? So we have a working electrode, we have a reference electrode, which is usually this one, and then we have a counter electrode like this. So most chemistry labs do this. So, and we can do many charge-discharge cycles, as noted here. We also do impedance spectroscopy, but because of lack of time, I'm not going to say much about this. I'm going to talk mostly about charge-discharge cycles. That's good enough to tell the story. Okay, so now we are ready to start looking at the data. So I told you why we went to lithium sulfur, and I told you the challenges with sulfur. And Then I told you how we make the battery, and the basically you can think of this as current because this has coulombs in here, and this is the voltage. So the charge discharge cycles look something like that. So the minute you make this battery with the lithium electrode and this sulfur, there is immediate voltage of about 2.5 volts because of the way the electrochemical potentials are for these materials. You immediately get a voltage. It's something like, if you take a lemon and you stick in the electrodes of the right materials, you immediately can get a voltage. You all have seen that video, right? Something similar like that. Yeah. We understand this in terms of electrochemical potential. So the first time you discharge it, that's the black trace. You get all the way up to more than 1600 milliamp hour per gram, which means it can store a lot of charge. And then when you charge it, and then you look at the second cycle, it immediately drops dramatically. And the fifth cycle, and if you go to thousands of cycles, which I don't show here, it will drop to 400 or even less. So this is at very slow charging rate, right? 1.1 C rate, and about 1 milligram per centimeter square area of sulfur. So obviously, more sulfur you have, you can store more charge, right? Because sulfur capacity is that amazing number you saw on the previous slide. But to make electrodes with more sulfur is also very challenging. Because if I make a slurry with a lot of sulfur and put it on an aluminum foil, it'll simply peel off. It won't stick. So that's another problem people found down the road after they got started working with this technology. So we want so ideally we want, even after thousands of cycles, we don't want this to move to the left. We want it to stay steady here. So in the initial studies, people want to understand why there is such a huge loss in the first cycle. Okay, in the first cycle itself, there's a dramatic loss of active material, which is the lithium, the sulfur. Both of them are suddenly becoming, or they are disappearing. So what's going on? So people have taken a deep dive into that, and they found out where this sulfur and lithium is getting trapped and resulting in the poor capacity in the first cycle. So this is another new terminology that people talk about in the battery literature. It's called the solid electrolyte interface, because as you saw in that animation, you have the electrolyte and you have the electrodes, the graphite and the lithium cobalt oxide. And right at that interface, you will get a passivation layer. So we can understand that using this cartoon here. So sorry, now there is some Chinese or Japanese there, but this is a beautiful slide, so I still decided to use it. So this is your salt, right? And this one, lithium, phosphorus, and hexafluoride. And then this is your ethylene carbonate. And then these are some additives. And this is your electrolyte. And so right at the interface between the electrolyte and that graphite, you develop a passivation layer. That's what people found out. And what is the composition of this passivation layer? It has a little bit of lithium, it has a little bit of the salt, it has a little bit of the electrolyte, all of them. So because you're applying a voltage or driving a current, there are some reactions where these electrolytes and salts break down and they form a compound and they deposit themselves on this anode. So the lithium that can go back and forth several times during charge discharge is the blue dots. Okay, so you can see there are several blue dots here, but some of the lithium turns into a red dot, which means it has formed a compound and it is trapped in, sorry, I told it wrong. The red ones are the reversible ones that can go back and forth. The blue ones are the trapped ones. So you see the blue ones are trapped, they cannot move out. So what this translates, or what does that mean, is basically that lithium is not available anymore to give you electrons to flow in the outer circuit. So that is dead lithium. So that's where some of the lithium is lost, and the specific capacity after the first cycle drops dramatically. So that's what people have found. That is only a tip of the iceberg. They also found that lithium is lost or due to a dendrite growth. So let me explain what that means. So let's say these are your two electrodes. This is a very zoomed in image. There is a separator here which we are not showing, but basically you have this is your anode, the lithium anode, and this is your cathode. And these experiments have been done under an electron microscope. Okay, so basically at t equals 0, the battery is just assembled. You then operate the battery for 31 hours, and as you keep operating these, you will see that small dendrites start to grow. It's much clearer here. You see those needle-shaped ones, and then even more as time progresses. And you see, ultimately what happens is that these dendrites short the anode and the cathode, and that's when the battery catches fire. Okay, so, and what are these dendrites? These dendrites are basically lithium. So a lot of lithium is lost in these dendrites also. So that is the second source. And then there is a third source where lithium is lost. So what has been found is that lithium has a tendency to make a compound with sulfur. So every time lithium enters the cathode, lithium makes these compounds that you see on the screen here, Li2 S8. So for every lithium, 4 sulfurs, and here there is every lithium there are 3 sulfurs, and for every lithium here you have 2 sulfurs, right? So something like that. So lithium and sulfur is also being lost, and this has a fancy name. So this is called polysulfide shuttle, and this takes place during charging, discharging. So essentially there are 3 main reasons why after the first cycle the capacity from 1600 it drops down to 1200, because of the solid electrolyte interface, the dendrite, and the polysulfide shuttle. Okay. All right, now that we understand what's going on, so can we solve this problem? How do we solve this? How do we prevent this loss in the first cycle? So basically, I'm showing you the same things I showed on the previous plots. So this is the one on the previous slide. This was a few slides ago, and this shows that sulfur exists as an S8 compound, and it eventually results in insoluble compounds like this, where both lithium and sulfur is trapped. Okay, so we want to now avoid this polysulfide shuttle. So, excuse me. So people have come up with a very smart idea. They said, okay, why don't we not use sulfur particles? Let's not use sulfur particles. Can we use some sort of a sulfur containing polymer? That way I don't have to use this guy. All I need is to use some additive and stuff like that. So, so this is again a detail. Let me skip this. This shows the chemical reaction with sulfur and lithium, basic chemistry. So let's go to the strategies. Okay, so the first strategy, like I said, is why don't we use some polymer-based materials, right? So they said, okay, obviously it will be good to have something that is conducting, and polyacrylonitrile, PAN, is a very good conductor that's made out of carbon. So what if I can take PAN and pyrolyze it? That means subject it to high treatment, high temperature treatment in the presence of sulfur, then it becomes what we call sulfurized PAN, or SPAN, SPAN. So replace all of this with SPAN. That is one of the suggestions. And then reduce the amount of carbon black. So SPAN will be 70%. This carbon black will be 15% or less. And then you still need some sort of a binder, although it is this itself also, because you're pyrolyzing it, it is quite brittle and becomes what we call pulverizes, becomes powder-like. So you still need some amount of binder, but much lower than what you would need with sulfur, let's say. And then you can make a slurry or a paste out of this and spread it onto 20 micron thick aluminum electrode. So this was one of the early suggestions, and it all looks good. So now I show schematically that this is the span. So I'm showing the span like this, and this is my lithium anode, and my electrolyte is here. So what they found is that if they use traditional electrolytes, like the ethylene carbonate that I showed on the previous slide, then after the initial cycle, they saw a little bit of dendrites and a little bit of polysulfide shuttle. But then after many cycles, these become worse and worse. And SPAN actually solved the problem only partially. It did not solve the problem completely. So then what else can we change here? You cannot change the lithium, right? You need lithium. You just change your cathode. What else is left to change? The electrolyte. So they said, okay, how about we try new electrolytes? Let's prepare new electrolytes. And the condition that we impose on this new electrolyte is that they should form excellent solid electrolyte interfaces. So you see this black outline here? So this is a solid electrolyte interface on the cathode. And likewise, this is a solid electrolyte interface on the anode. So if I can create these nice passivation layer on my anode and cathode, and then I will get very little dendrites or no dendrites, even in the initial cycle and after many, many cycles. Okay, so that is the challenge. And can we really do this? So we have to now switch gears. Instead of thinking about electrode chemistry, now we have to think about electrolyte chemistry. So electrolyte chemistry, what is known is that if you take carbonate-based electrolytes, then they favor a growth of the solid electrolyte interface on the cathode. This is very well known in the literature. Therefore, the anode, the dendrites grow like gangbusters. The electrolyte cannot prevent this part. And on the flip side, it is also known that if you have ether-based electrolytes, they favor a growth on the anode. See, there are no dendrites here, right? But this cathode gets worse. So basic logic tells you is, what if I mix these two guys, right? So let's call this traditional electrolyte 1, traditional electrolyte 2, okay? So electrolyte 1 is favorable for the anode. Traditional electrolyte 2 is favorable for the cathode. So can we mix them and get some synergistic effect? What that means is that TE1 in the presence of TE2 and TE2 in the presence of TE1 creates what we call a bilateral solid electrolyte interface. So this is unilateral because it's only doing on the cathode or only on the anode. But if I mix these in the right proportion and if I use the right salts, can I get this magically, this bilateral SEI? Okay, so that's what I did with my collaborations in China. So here is the big picture. So the big picture to develop this new electrolyte. So we start with the traditional electrolyte one. Like I said, it is good for the anode. The traditional electrolyte 2 is good for the cathode, right? And so it is basically this salt and this organic solvent. So, they are all explained here what DME is, dimethyl ether. This is dioxylene, DOL, and likewise over here. So we did not, we did not get bogged down in the details here. But you can see that it is a salt in a composition of electrolyte. This is a salt in a composition of electrolyte. So when I want to mix and match, the permutation combinations are huge. They are about 10 to the 6 if you work out the number. More than 1 million. So how do I know which one to start with? So with my collaborators in China, we were able to do only 60. We prepared 60 compositions as best guesses, and we did that by and created what we call new electrolyte 1, and we found that it does bilateral SCI on both electrodes. And this new electrolyte 1 has not just this salt or this salt, it has a combination of both salts, and it has all 5 of these solvents. You see 1, 2, 3, 4, 5. Here you have 2, here you have 3. So we found this does a good job, and then this is not the end of the story. If you work harder, you can discover more compositions that form bilateral SCI. But just forming bilateral SCI is not the end all, right? You want the battery to cycle well and so on. So long story short, we found this Ne2 as the best. And this, like I just mentioned, I call it the brute force method, just, hunch and knowing basic chemistry, what works and what doesn't work. Just like how we know that oil and water don't mix, right? Basic knowledge. So we went by basic knowledge to identify 60 compositions, and we tested all of them. A lot of work. It took about 3 to 5 years to finish this study. And let's see, let's move on to the next slide here. So next slide shows you the data. Yeah, but so before I dive into this data, what I want to tell you is that now we are using machine learning to guide us. So that is the current level of current status, because machine learning is becoming very popular. You can teach algorithms to look at the energy levels of these electrolyte compositions, and you can put some boundary conditions and try to get the best compositions for the machine learning algorithms to tell you. Okay, so that is our current status. So let me tell you or show you why Ne2 turned out to be the best. Okay. So here I'm plotting the amount of charge that it stores, and this is the number of cycles. This data goes up to 500 cycles. Pretty decent number of cycles. And then you're seeing another new terminology here, right? Coulombic efficiency. So Coulombic efficiency is very simple. Basically, it means the amount of the ability of charge to go back and forth and not get lost. Okay, so most of the time it is about 100%. It's definitely about 90% in most cases, because in the first cycle, when we lost from 1600, the capacity dropped from 1600 to 1200, right? that is called conditioning. We are basically conditioning the battery. There is no way we can completely avoid it. There will be some loss, and after that, most of the lithium ions do survive. Okay, so that's why this Coulombic efficiency is pretty high. But it doesn't mean much, because when you actually measure the capacity, you still see that, like with this is the traditional electrolyte. The traditional electrolyte 1, which is good for the anode, see, the capacity keeps dropping, and it is almost nothing here, about 100. So this is not good. And TE2 is holding fairly well, but still it's not very high. Any 1 is better. Any 2 is like rock solid and more than 1,000, right? It's around 1,200, which is amazing. So yes, so the bottom line here is that span, which has a sulfur content in it of about 42%, and at a slow charging rate, it does very well. So this is due to the formation of the bilateral, much better than having a unilateral SEI, or solid electrolyte interface. Okay, so these 2 are with unilateral, and these top 3 are with bilateral. Okay, so this is a new strategy to improve lithium-ion batteries. Okay, all right, I just told you what's and how do we know that the polysulfide shuttle is mitigated? So you can actually go back to the 3 electrode setup, and if I use my traditional electrolyte, sulfur comes into the solution, it immediately turns yellowish. With the new electrolyte, it still remains transparent. So this is one simple way to show that the polysulfide shuttle is mitigated. All right, so now what about charging at high C rate? Remember I said we want to charge in 15 minutes, which is about 15 C. So if I look at the traditional electrolytes, which is the black one and the red one, so see that this doesn't even survive many, 250 cycles. The battery dies after this point. We cannot make this work. Traditional electrolyte 2, not bad, but very low, extremely low. And the new electrolyte 2 is up there. It has, you will notice that it dropped from 1200, the capacity dropped from 1200 to little over 800. And that is normal, because if you have a battery and you're trying to pull or charge it fast or pull charge fast, then its capacity or its ability to give you useful charge goes down. Okay, so that is pretty typical. And also you'll see so these 3 plots, the axis is here, Coulombic efficiency. It also takes a hit. It starts going down. This is 75, so it comes little over 80 and so on. So it is tough to make a battery that can charge at a very fast rate. 15 C means 4 minutes. And it is still surprising that because of the bilateral solid electrolyte interfaces, this battery did not catch fire. It did work. Okay, so what about shelf life? So of course, you cannot run an automobile with 1 battery, right? So, but you can definitely light LEDs. So you see, we lit 2 LEDs. This is the starting, 1 hour, 2 hours, 3 hours, all the way up to 10 hours. The battery discharges over 10. So we charge it in 4 minutes, and we discharge it over 10 hours. That's pretty impressive. Okay, what about shelf life? So see, we are getting 1200 milliamp hour per gram, right? And it stays rock steady over a number of cycles. But what we have done is we have actually stopped the battery and let it just sit there. So because we want to determine the shelf life. So we interrupted the charging, discharging for 1 day, 24 hours, for more than 1 day, all the way up to 10 days or 20 days. This is 20 days. And every time we turn it on, it does come back close to what the value is. So the shelf life is also decent. And here we also change the temperature. We put it in we put it in contact with an ice bath. So this is how the industry tests batteries. A lot of testing goes in before the battery comes into commercial market. So when you warm up the battery, the coulomb, the capacity goes up again here. So long story short, again, I think this battery with the bilateral solid electrolyte interface and using this new electrolyte does a pretty good job. So what else can we do? So like I said, if you put more sulfur, it's good, but then the sulfur doesn't stick to the aluminum, right? It peels off. So why don't we make the aluminum foil hollow? But hollow aluminum foil is okay. It tends to oxidize. So rather than that, why don't we use a hollow carbon foil? Excuse me. So hollow carbon foil, people have done a lot of work with porous carbons. And one such thing that we have done in my lab is what we call the graphene foam. Graphene is one layer of carbon, and they are basically, they can hold a lot more sulfur. As you can see, we can put about more than 3 milligram per unit area. And the beauty is that even if there are cracks in the span, so the covered area is the span, okay? Wherever you see covered area, like here, it's span. And these are the open areas, these are the covered areas, right there. And whenever you see cracks in the span, all these can still be utilized because they are connected by this graphene framework, okay? So no amount of sulfur remains unused. That is the biggest advantage. And we actually proved that. This is going to be my last slide. So again, we are showing you voltage versus capacity. So as we increase the aerial capacity, so let me slow down a little bit here. So this is, if I use aluminum foil, the open circle, and you see the amount of sulfur utilization is down there. So I have to put a lot of sulfur to get a very high capacity with aluminum, and I can't do that because it will start peeling off. So there is a big roadblock with aluminum foil. But with graphene foams, because I have a lot of open structure, as I pack more and more sulfur, I can push this aerial capacity to more than 20 or close to 20. It's about, there is one more data point that's not shown here. It's more than 20, about 22%. So what does that mean? So let's understand that. So what that means is that this is a little bit of a busy slide. So let me take my time to explain. So I'm showing you aerial capacity. This axis is now plotted as the y-axis. And I'm showing you the amount of sulfur loading in there. So let's just take one data point here. So the plus signs that you see there are the data points by other people's work where they have used different kinds of porous carbon. So let's just take this one. So what this is telling me is that these guys, the authors, were able to get a aerial capacity of about 15. Remember, the name of the game is to increase the amount of sulfur loading, right, or aerial capacity. So they had about 20 milligrams per centimeter square, so basically, right. So they were able to get this with 76% of the sulfur in their cathode. whereas we were able to get aerial capacity of 20 with only 22%. So in other words, our sulfur utilization is much higher. So if this is 25, this is 75, we are using only 1/3 of the amount of sulfur to get the same results as other people got. And that is because of the graphene form, the porous porous electrode. So why is this important? Because remember, it will bring down the weight of the battery. So let me sum up by saying that I have presented to you 4 strategies. If you were taking note or paying attention, you will see there were 4 strategies. One is the solid electrolyte interface. The other one is the mitigation of the dendrites, making the bilateral solid electrolyte interface. And then the other part was the bilateral interface reduce the polysulfide shuttle by making span. And the last one I just showed you is by making porous electrodes. So these are the 4 strategies that will actually help us make better lithium batteries. So with that, I thank you for your attention. And I must thank the federal funding agency that funded this work at Clemson. And then, of course, I did none of this work. Everybody in my team did this work. So this is my team at the Nanomaterial Institute. And the person standing right here is my mentor. She was my mentor at MIT. She visited my labs a few years ago. She just passed away, unfortunately. Her name is Professor Millie Dresselhaus. And and here is a faculty member, Rama Pudila, and another faculty member here, Shriparna, and rest is my former students and current students. With that, I thank you and turn over the mic back to Benoy. Sure. Okay, let me see if I can stop sharing the screen and see you. Give me a second. Yeah, okay, good. I can see all of you now. Sorry, what was your question again? Right, right. Yeah, okay, very good question. So you have to go back to that spider plot. So, like I said, we published 2 papers with aluminum ion batteries. And the problem with the aluminum ion battery is the electrolyte that is needed for an aluminum ion battery is extremely expensive. And in the spider plot, one of the metrics is cost. So we don't want who will buy a very expensive aluminum battery? Nobody will buy it. So the industry is not interested yet, unless we use machine learning and try to come up with a new electrolyte for aluminum, like we did for the lithium sulfur. There will be hardly any interest. Yeah, absolutely. So graphene is a new form of carbon, right? It is just 1 atom layer thin graphite. Very difficult to make it in ton quantities. And therefore, again, the cost is very high. So, but carbon fibers has been around for more than 50 years. And with carbon fiber technology, People have made carbon sponges, carbon foams. And the beauty about carbon is inherently conducting material, so you need less amount of carbon black and so on. So to answer your question, yes, there are others, but they are those porous carbon structures, like I showed you, don't allow good utilization of sulfur. So this is still a work in progress, and currently my team is submitting proposals. We are partnering with folks in Kentucky, and we are partnering with folks in Delaware to use different resources, because each team brings a special skill set to the problem. And what we want to do is to try to improve on this lithium sulfur battery, because it's like a race to the finish line, right? So based on the study that I just presented, we think lithium sulfur battery has a greater chance to get to the finish race compared to the lithium air or any of the others that you saw, or even the aluminum ion battery. So some of them are closer to commercialization, and we feel lithium sulfur is one such. We could be wrong, because who knows, when you scale up, we may see additional problems. We don't know. And but we have to take a chance. So we are promoting lithium sulfur as opposed to aluminum ion or any other chemistry or any other electrodes also. We will try to make, just like we try to make new electrolytes, we'll try to make new electrolytes. We'll refine that using machine learning. There may be a better combination than the 60 combinations that we saw, because we were doing by brute force. And then we'll also see if we can do something like dope the carbon foams to make them better electrodes and so on. So there's a lot of work, and I see a lot of students here. So let me give a shout out and say that if anybody is interested in these technologies, please contact me, apply to Clemson, and we will train you so that you get your PhD in battery technologies. Yeah, okay. So it is a little premature to answer that question. Why? Because nobody has made a battery pack with lithium sulfur batteries. And so that is number one. Number two, Tesla is the king right now. So what I mean by that is, see, every battery has a format, right? So battery, let's take the ever-ready battery, for example. It looks like a cylinder and it's good. But Tesla has so much money and so much resources that they have already transitioned to a different format, which means that their battery looks more like a box, you know, rather than like a cylinder. It's not even like a pouch. It looks more like a box. Why? Because then it can store more energy. More energy translates to less number of cells. So what I'm trying to say here is that there are a lot of uncertainties here, and with the lithium sulfur battery technology, while at the same time, Tesla has already made a lot of progress, which is highly proprietary. So we don't know. So what may turn out at the end of the day is that the lithium sulfur batteries have advanced to a certain point, But Tesla is so smart that they have already reformatted the design of the battery that still the lithium ion battery may be better than the lithium sulfur battery for automotive industry. That's why people like us have to team up with other states, other researchers in Kentucky and Delaware and so on. So we want brighter minds on my team. Okay. Yeah. So my experience on the first day, I said, I was a little bit lucky because I had an opportunity to spend my Christmas holidays at BARC, Bob Atomic Research Center. In those days, this was like what, 1980s? No, yeah, 80s, I think, 1980s. In India, digital electronics was the every smart kid wanted to become an electronics engineer in those days, and I was one of them too, unfortunately or fortunately. So I at BRC, the project that they assigned was to build a digital clock. So we had to program and a couple of things. So why I'm telling you this is, but see, today I'm a hardcore physicist and not an electronics engineer. So so from my experience, what I find is that when you're doing undergrad studies or even grad studies, your vision is kind of narrow. I don't mean to say this in a demeaning way. I'm saying this because you haven't had a chance to explore the other options yet. That's the reason I'm bringing this up. And when I came to US, I could have gone into electronics, but then I saw that physics is the underpinning all technologies. So why would I want to narrow my expertise and become one sort of an engineer? I thought now as a physicist, I can work in several different areas, and we are working with you name it, we can get into that technology. So I enjoy that much more. And so my advice to students is, have an open mind about science in general. And I know in India, a lot of students want to become engineers because that's where all the jobs are. And I don't blame them for that. But also now Indian government has recently reached out to the Indian diaspora like myself. And we are telling Modi's government that, research should not be compromised. And you will be seeing more and more opportunities in India for research. So that's my 2 cents suggestion. Enjoy what you're doing and don't undermine the power of basic sciences. Okay. Thank you all.
Thank you, sir.
Bye.
Thank you so much. I'm doing it. Okay. All the other students have left. The department members alone remain now. Well, sir, thanks a lot. It was really resourceful, and thank you for guiding them in their initial years. Like many of them have been reluctant to join in this physics actually. They were all targeting for the engineering stream or medical stream. And in their first seminar, they are basically sitting here half-heartedly.